The first recorded evidence of compressional structural analog modeling being used was in 1812 by Sir James Hall, who used these models to investigate folding of sedimentary rocks. The type of analog model we are using today is sandbox modeling to test for compressional tectonics. By using sandbox modeling, we are able to understand complex, large-scale, and long-duration geological processes and events, like mountain belt formation and other compressional tectonic events. This is achieved by using sandbox models, as they allow us to speed up geological processes that would happen at a slower pace in real lifetime. In today's experiment, we are looking at how the presence of a salt-based layer affects generation of thrust faults. The hypothesis we would like to test is that the inclusion of a glide plane made of talcum powder will affect the faulting that forms in the experiment. The hypothesis we would like to test is that the inclusion of a glide plane made of talcum powder will affect the faulting that forms in the experiment. We are using talcum powder as an analog of salt tectonics effects on stratigraphy found in places like the Salt Range in Pakistan.
In our second experiment, we used talc as a basal layer and sieved out the talc and measured the layer as 1 mm thick. We then sieved out the sand and measured out 3 mm thick layers of alternating normal coloured sand and black coloured sand. Continue this until you get a reasonable total thickness, in our experiment which was 4 cm. Place a ruler/tape measure at the bottom of the sandbox, which can be used to measure and record the distance that the wedge is shortened. Ensure you have a device set up with video facing the sandbox to film the experiment being undertaken. Once the experiment is set up, ensure you are ready to film the experiment and systematically observe and record data. Data that is recorded is the amount of shortening, position of locus of active faulting, match wedge thickness, alpha, number of faults, dip of youngest and oldest fault, and the interlimb angle. Now with the experiment explained, it's time to talk about the findings. During the compression of the sandbox models, there was an interesting result with the thrust formation in the talc experiment. Not only did the talc experiment produce 2 thrusts after 2 cm of shortening, the angle of thrusting was at a steeper angle. This trend continues through the experiment, where on average the angle of thrusting is steeper and an increase of thrust forming with a talc layer added. The talc acts as a glide plane for the lowest sand layer, allowing thrust to propagate at steeper angles, leading to 2 thrusts forming, as the fault is created from pressure caused by the first fault gaining friction from faulting onto the sand layer. An interesting feature of the experiment talc layer is the addition of a structure known as the salt pillow. This feature, as seen here, has propagated between the layer of sand and has a noticeable steep dip compared to the surrounding sand. Looking at these results, it is clear to see that our hypothesis of salt decalment affecting fault and fold propagation is proven by our results, with how the quantity and steepness of faulting has changed with the addition of a glide plane that mirrors how evaporate function in faults. But we should see some real-world examples first.
There are many examples of salt in orogenic settings. One of the most dramatic is the Salt Range in Pakistan on the hinterland of the Himalayan orogeny. This region is dominated by salt deposits combined with marls, sandstones and carbonates. The salt in this range acts as a decalmant similar to our experiment, which allows for the generation of a complex fold and thrust belt by separating the overlying sedimentary sequence from the crystalline metamorphic basement, allowing for thin-skinned deformation of these sedimentary rocks. This increased structural complexity combined with the elevated stress regime of an active mountain belt makes the Himalayas one of the most tectonically active regions in the world. Also of note is salt's more economic properties. Aside from being a commonly mined commodity in its own right, the impermeable nature of salt makes it valuable for trapping hydrocarbons within reservoirs, often at the sides of salt domes. And also it allows hydrocarbons to flow more freely through a faulted crust. In conclusion, our experiment was a success. The structural data collected from this experiment proves the effect that salt, or indeed an analogue of it, impacts the generation and complexity of structures within a compressional setting. This experiment, however, is not without room for improvement. It could have benefited from repetitions of the experiments to remove outliers within our dataset. We also believe that had we made our salt décollement layer thicker, it may have provided better data, as well as if the sandbox were longer so we could apply more shortening in the experiment. We hope you enjoyed our video and maybe learned a thing or two.